Okay, good afternoon, everybody. The topic of today's webinar is the new Golang client for Hazelcast in-memory data grid. I'm Neil Stevenson from Hazelcast. If you're watching on YouTube, a minor point is that this webinar is recorded in March, which comes out in some of the examples. Basically, what we're going to look at today is what is an in-memory data grid? Why is that of interest to a Golang developer? We'll then have a look at Hazelcast Golang client. We'll run into demonstration, and then there'll be a summary at the end with a chance for question and answers. So Hazelcast itself. Hazelcast is an organization, a company. We have two software products called Hazelcast IMDG, in-memory data grid, which is the topic of today's webinar, and Hazelcast Jet, which is a streaming analytics engine, which we won't cover today. Hazelcast, the company, we were founded in 2008. We've been got offices all over the world. I'm speaking to you from London. Our head office is in Palo Alto in California. And our software, it's Apache 2 license. You can go to the hazelcast.org website. You can download it from GitHub. You can do things with Hazelcast. And if you want to, we have commercial support. So you can have SLAs around support contracts. You can have enterprise features, which are available as additions. So an in-memory data grid, what is it? Well, it's a grid, it's data, it's in memory. If we take these three things in reverse order, it's a grid, it's a collection of processes which join together to form a cluster, a group, act collectively to provide services as a group, as a whole, and these services are spread out across individual processes. So there's a variability in the size that comes in there. You might have a group of 5, you might have a group of 6, you might have a group of 5 and change it to a group of 6. So it's a collection of processes, it's a team. It's about data, it's a data grid. We are storing data in these processes. They all try and take an equal share of data storage. If you're doing data processing, they try and take an equal share of data computation. And there's data messaging. You can send messages from process to process. So those are the three kind of key parts of a data grid. Obviously, the most important part is the data. If you don't have the data, the processing doesn't have so much to work on. And then the last part is the in-memory component. This data is stored in the memory, in the RAM of these processes, rather than on disk. This gives you tremendous advantages of speed because you have faster access to memory. You're not waiting on rotational disks or SSD disks. The memory is faster than disk. Is just a feature of it. And this data is, in Go terms, it's structures, it's basic objects, it's not tables, it's not a relational system, it's holding the data you want. So you don't necessarily have translation mechanisms between tables into structures. You're just holding it in structures. You have it as you need it. So Hazelcast IMDG, I mentioned earlier about the scalability. You might have 5 processes in your grid, in your cluster, change it to 6, 7, 8, 9, 10, you just keep going up. It's a resilient system. People are, when you store data in memory, people are kind of a little bit nervous of memory and very confident about disk, and those two things are not right. Memory is as safe as you want it to be. Disk is as safe as you want it to be. We'll come back to that in the demonstration. The cluster itself is written in Java. So although we're connecting to it from Go, the cluster we connect to is written in Java, so it's Java processes. That makes life very easy if you're doing server-side processing and you're a Java developer. If you're a Go programmer, that's obviously not ideal, but it's a lot easier than writing stored procedures on a database. And it's very widely used. If you look at the Hazelcast website, there's a listing of a number of our customers that give you by sector breakdown of here's some banks that use us, here's some telecoms firms, governments, and so on. And where we're going to look at today, the key data structure we'll look at in Hazelcast terms is usually referred to as a map. A map is a mapping from data keys to data values. It's a key value store, it's a dictionary, it's a lookup table where everything has an identifier that you can find it, and then more data associated with that identifier. These keys and values, in the example today, it's a mixture of structs and primitives, but you know, it can be whatever suits you. These maps are named, so you can have several of them, as we'll see, and you can partition this data across the processes. So what that means is if you've got a cluster of, well, let's say 5, then each of those 5 processes has a 5th of the data. If you scale up to 6, then each has a 6th of the data. So you can keep adding processes to increase your capacity. And the data is striped, partitioned, spread across these processes. Each has a share. That allows the cluster to hold more data than each process individually can have. So that gives you that lovely niceness of scalable storage. You don't really worry about the capacity limit of one process because you've got several. They're all taking a chunk of the work. And typically you mirror this data. So you have a configurable level of backups so that you can decide that if a process goes off the air, its slice of the data might be backed up somewhere else, and usually is. So you're not particularly worried if something has a hardware fault or any kind of crash. So this gives you that kind of resilience on your cluster. So it's time for a picture. So what we have here is a representation of 4 processes, 4 towers, silos, whatever you really want to call them. These are Java processes, so these are JVMs. These are 4 Java processes, which doesn't actually show in this diagram whether they're on the same machine or different machines. Each of those is holding an instance of the in-memory data grid. And then at the top, we have 7 light green containers for data. And the data in this example is playing cards. So what we see is the second process on the left in part 1 of the data space has the 3 of hearts. And the first process on the left in part 4 has got 2 parts of the data. So you chop the data space into available parts, and each of these parts might have some of the data. What you find is it scales up as this spreads out nicely. Now in this diagram, we've sliced the data space into 7, and we've got 4 data processes. So it doesn't actually work out evenly, but that's not really a problem because 7 is just an artificial number for this example. More usually, you go into hundreds for the number of containers. And then if you're dividing that across 4, then some will have maybe 50, some will have 51. The numbers even themselves out at larger volumes. So what we see here is at the top, there are light colored containers, which represent the primary copy, the master copy of the data. And then at the bottom in a darker shade of green is kind of like a shadow mirror copy. So the data on one process has a backup copy on another process. By default, Hazelcast will control where that is, and then you can help if you know extra information that these processes are on machines with different power supplies or whatever kind of aspects of the physical infrastructure are relevant to you. And then the nice part here is your Golang routine can connect to your grid and retrieve data much as you would retrieve from any other kind of system. Now, in fact, grid is multiple processes. So what you do is you open multiple connections to all the processes on the grid and use intelligent routing to say, I want this item and it's over there. So I go directly to the process that has it. So you never have more than one crossing of the network to get a piece of data, unless you want that. And as we'll see in today's example, there's various other technologies that can connect to Hazelcast, Node.js, .NET, Java itself, of course, Scala, number of ways. Today's example is obviously on Golang, but we'll sneak in Node.js just to show interoperability. Having said it, it's a map. Here's a little piece of Go code. The sweet spot for Hazelcast is this direct retrieval. We have a map here, which is called people. So we get a reference to the map and we can get the item with the key nil. So go and look up that piece of data. Similarly, we can do injection. We can put data back into Hazelcast because reading's not quite the end of the world if you can't do writing. So map get and map put are the terminologies for reading and writing. And that's great, but sometimes you don't have the primary key. So you want to do searching. So you might look for all people that have the age attribute of more than 65. So that's basically saying I'm wanting somebody who has a structure that has a field called age, and it's a numeric field and the value is greater than 65. Fairly obvious kind of querying. Where this works well is this querying runs in parallel. So if you've got 4 processes, then each searches their quarter of the data. And it happens in parallel on all the processes at once. So your search time is spread across the data, divided by the data. Divide and conquer kind of approach. Now, what you can also do on the server side is you can do a bit of processing. You can run code. Remember, the server side is Java code, so you can do execution on the data rather than retrieve the data and update it and save it back. You can just send the processing to the data. And again, this can run in parallel if you're doing some sort of update across multiple data records. I will remember this is Java code, but we'll see if we can kick it off from Go. And then the last part of the section is that you can do a kind of trigger processing. You can have Hazelcast alerting you when changes happen to your data. So something is deleted, something is inserted, something is updated. Very easy coding, but very kind of powerful. You can be notified of change. And if you're in any kind of microservice or distributed architecture, it's useful to know when one process has done something. It's a way of saying, I want to tell you that something's been done. We can do that on a reaction basis. So Hazelcast clients, you can connect to the grid from these technologies. And obviously, the one in the bottom right is the one we're interested in today, the Golang client. So the Golang client itself, we launched in January. It's currently version 0.1. It has all the basic kind of stuff for Hazelcast activity. We can connect to the grid. We can determine when things are happening, members are starting, stopping, that kind of stuff. We can connect across all processes. That's what we call our smart connection. Or if you want, you could just connect to one of them and use it as a proxy to get to all the others. And we have our map data structures, which we'll have a look at. So we can run across data across all the grid and have a look and see what it's doing. So demonstration time. Obviously, this will feature Hazelcast in-memory data grid. It's obviously going to feature Golang, and just for fun, we've also sneaked in MySQL and Node.js. The application here is not particularly realistic. It's an online shop that sells nuts. You've got to have a demo of some kind, so that's what it's going to be. So let me close down my slide deck temporarily. So here we are, Marzo, the word for March. Let's start with MySQL. Let's see. I'll connect to a MySQL system that I've got running on my laptop. And what that does is that sets up my example data for this demo. And this is an SQL table. So what we can see here is our stock. So we have in this SQL table, our shop is selling 7 different kinds of nuts, which have got various prices and various stock quantities. We've got 50 almonds and there are 66 fractions of a unit each, whether that's dollars, euros, whatever, is up to you. So there's our data. Now what I'll do is I'll start my Hazelcast grid, and it's a Java process. So I will, for the purpose of today, run 3 of them in 3 separate windows. 2, 3. So this starts 3 Java processes on my laptop. They will network together, they will find each other, and they will form together to form a grid. We see a few messages coming out from Hazelcast as here's connections forming between these 2 processes. And this is the message we're looking at for in yellow, that our grid has got 3 members. They're running on ports 5701, 5702, 5703. As a little bit of an extension, I've also added an HTTP listener to my process, so we can have a look at what they're doing. Now, the first thing I'm going to do on here is run a little command I've added called data, which tells me what data is in the grid. So I have configured my Hazelcast so it will load data from MySQL. So what I have here is the same data in memory as was stored on the MySQL database. Because you've got to have a way to get the data into the grid, and that's the way I've chosen here. So if we connect to this Hazelcast cluster using our monitoring tool, the monitoring tool is in the commercial edition. What we see is my data is split into 3 across 3 processes. Here's the 3 processes. If I click on my Hazelcast map called stock, I can see there are 7 data entries. 4 of them are on that process, 3 of them are on that process, and there are 7 backups. So everything has 1 replica copy somewhere else. So the 3 records that are here might be backed up onto that one or onto that one. Just giving the counts at this level because this is all we're kind of interested in. So let's take a quick look at the data. I mentioned there's my HTTP port. So if I look on a REST interface that I've added myself, there we go, there's some data. So the cashew nuts, the price is 2, we've got 25. And if we look at the raw data, there it is as a nice piece of JSON, or ugly piece of JSON, depending on your view of JSON. So that's my Hazelcast cluster. I've also added an extra command to my REST queries to get me all the ones that contain the letter H, so which is currently pistachios and cashews. So it's time for a little bit of Go. So I have a Go routine here. This isn't doing anything with Hazelcast. This is just connecting to my SQL database and running a data SQL query. There you go. There's the same data that's in SQL. I can access it from Go. So all very well and good. First thing we're going to simulate is our SQL database fails. There we go. My SQL instance is stopped. So now if I run this same command from Go, can't connect to the database. Disaster. We only have one database and now it's failed. And just for added proof, if we do the same from MySQL connector, you can't connect. It's not working. So that's not great. But let's have a look at my code now. So let's, I promised a little bit of a mention of other technologies. So let's start with Node.js. We can push in data from other technologies because you might have a variety of technologies in your setup. But don't worry too much about the code here. This is a Node.js function that our stock item has got a couple of fields, and all my function is doing is send the name field, send the price, send the level. This is how you inject data into your Hazelcast cluster from Node.js. You have a method to read data, you have a method to write data. Dead easy. Topic for today isn't Node.js, but we need to see something else. So one more down. So my Node.js script, what it does is it connects to Hazelcast. It creates a stock item for hazelnut. I mean, how could we miss that one out of the stock for stocking nuts? And what it does is it puts, the key is hazelnut, the value is hazelnut, and we stick it into the stock map. So if we run that from Node, then what we get back is, here's an item of stock. We're not Node programmers, so we won't really know too much what that means. But what we'll do is we'll now see that we now have 8 items in our Hazelcast cluster. If we look on the console, if we go to one of the processes, and now it's got all sorts of exceptions because it can't connect to SQL, because the SQL server's down. So what I'll do to stop that message occurring is I'll start the SQL server. So now Hazelcast can connect to MySQL. So it will stop moaning about missing connections. And now if I look at my data in Hazelcast, I will see there are 8 entries because we now have the hazelnut added. So that's jolly good. If I go back to MySQL and use the parcel and have a look at the stock map, we can see that hazelnut has now appeared in the stock map. So if you remember, the MySQL instance had, well, I pretended to make it fail. I've written data into the Hazelcast cluster. Hazelcast is just holding on to that data and saving it down to MySQL when the MySQL comes back. So an outage on MySQL doesn't necessarily cause an outage on your application. As long as you're talking to Hazelcast, you have this intermediate layer that is resilient. So we're all happy there. So that's what happens perhaps if your underlying database technology has a mishap, which you don't really want to happen, but you have to plan on these things. So let's plan on a mishap on Hazelcast now. So if we look at our Hazelcast cluster, what we'll see is that the first process has got 4 of the master copies. The second process doesn't have any. The third process has got 4 of the master copies, and the backups are spread across. So what we're now going to do is we'll simulate a failure on Hazelcast. Let's take that one for no particular reason. I just cancel the window. What we'll see, that the window we're now seeing is one of the other processes. So it's now noticed that 5702 has gone off the air. 5701 is still running. 5703 is still running. If we look on the console, we'll see that we still have 8 data records. We have 4 here and 4 here, 4 backups on the other way around. if we were to run my data command, none of the data's gone. We've just lost the process. Because it's mirrored across the others, then that's not really a problem for us. But we wanted 3, so let's get back to the 3. Now, just while that's heating up, if we have a look at my REST interface, I can now look for nuts that have got H, and hazelnut has now been added to pistachios and cashews. So we now can see all the data we want. So it's now really time to have a look at some Go coding, because that's the whole point of this. Hopefully you kind of seen that the cluster itself is resilient to certain levels of failure. You can, if you've got a cluster of 5 and one process dies for some reason, you've got a cluster of 4. If it's 4 and one dies, you're down to 3. The only problem is when you're 2 and it drops down to 1 and 1 down to 0. You need to configure it for the number you kind of expect to fail. If you're expecting 1 to fail and you need 5 for viability, then you should run 6. Not the hardest thing in the world. So, time for some Go coding. So, if we have a look at my Go code here, what we're seeing is how do I connect to Hazelcast? I give my Go routine the address, host, and port of some Hazelcast processes. It's not realistic to list them all because the cluster might grow and reduce in size. All you need to do is find an answer from one of them and it tells you where everybody else is. So if you've expected that your cluster can survive with 1 missing, then you need to list 2 processes. If you're expecting it can survive with 2 missing, then you list 3 processes. So you always need somebody to give you that first answer. You find somebody in the team and it tells you everybody else. So that's all that part does. Then what we do in this example is we look up the map that has the name stock. We run the key set operation. We're only interested in the keys of the map, the identities, if you like. And then we just print them out to the screen. And then because we're nice, we shut down cleanly. So if I run that, then what we get is, oh, count is wrong, but because I didn't increment the count. But we see there are 8 nuts. Those are the keys. That's fine. That's all well and good. That's a lot of the way. We can now get at data from a Java grid that we know is resilient, scalable, all the kind of nice stuff, and we can access it from Go. So that's great. Let's do some more things now. So example 2. So the configuration is just the same as before. We're just connecting to Hazelcast. We're getting at map. This time the map is called alert because the maps are named. And what we're going to do is we'll take the time and we're going to create special offer on our maps. We're going to say walnuts are half price. And we will put that into the map. The way the put operation works is it actually returns you the previous value, if the previous value exists. So let's run that. So we have inserted the value walnuts are half price. If we run it again, it now tells us that walnuts are, we've changed the value from walnuts are half price to walnuts are half price at a different time of day, a few seconds later. So that's kind of good. If we go to our management center, we can see the alerts map. The alerts map, the way I have it configured is I've not bothered to have any backups. So we have 1 data record, which happens to be on this process, and there are no backups. You can decide if you want backups or not. Your data is as safe as you want it to be. You could have 2 backups if you wanted. In this case, I've gone for 0. If I lose the price alert, I don't particularly care. So If we have a look at our grid, now I need to find which one it's on. That data is on process 3, which I think is that one. Here we go. So what we're getting out of the grid is I've added a piece of Java code that's logging when things are happening to my data. So my data has been added to the grid. My data has been updated in the grid. These were the things that the Go routine did. I injected data. And these are things that I've got Hazelcast to do. I've got Hazelcast to delete the data on a time basis. So the data expires. You're getting Hazelcast to throw it away, in this case, after a minute. I'll show you how that's coded in Hazelcast because it's trivially easy. So my map is called alerts. I have it configured with no backups, as we saw. I have it configured to keep data that is idle, as in unused, for 60 seconds, and then it can be deleted. It's data we don't need anymore. And I've added a listener that calls a piece of code when something happens to the data. And if I look at that listener code, generic logging listener, what this does is when a data entry is added or a data entry is evicted, eviction is removing it from memory by Hazelcast. You can do it explicitly or you can let Hazelcast do it. Then it does this logging to the screen. So that's good. So what we see is that data has been removed. So our alerts map is empty. We can see the size of that map has dropped from 1 to 0, unsurprisingly. So now what we're going to do, we have another Go routine here. So what this is doing, same stuff as before, connecting to the map, but now we're adding an entry listener on Go. And what this means, if I have a look at this listener code, is this is the pattern. We're getting a wait group, and every time an entry is added, then we're just doing a FIMP print line. Every time an entry expires, we do a FIMP print line. Every time an entry updates, we do a FIMP print line. So if I run that, that client starts up, connects to the grid, and waits for something to happen. If I go to my grid and run my command clients, I can see there is a client connected. We have one client, hurrah. And now, if we're back here, we do our data insert. We've injected a piece of data onto the grid. As we saw earlier, the grid will notice, where is it? There's the grid noticing, price alert has been added. But what we also see is that a Go routine can know about this as well. So this is great for any kind of shared data in microservice land. You don't necessarily want to share state, but if you do, you can have one microservice creating data that another is listening to, or so on. So that's what that does. Walnuts are half price. Wait, that's good to know. Maybe. So we've got a couple more things to see, but let's just take a look at the time. So 16:51. Right, in about 12 seconds, that data will expire. And what we should see is the listener detect that the data is expired and fire a message, because you might be interested in that. This offer is no longer relevant. Here we go, data's expired. When it's expired, it's deleted. You don't have the value because it's been deleted. That's fine. So, time for a little bit more. We want to mutate some data now. So here's our mutation. This time we're going to change almonds. Off the top of the screen, the same stuff about connection. You obviously maybe want to import that, but we get hold of the map for the stock. We retrieve the information for almonds. That returns us a stock structure. What we do is we change the level for almonds. We've reduced by 1, we've sold an almond, and we save it back. If we just have a look at the data model, the stock structure looks like pretty much the same as Node.js. It's like it's got a name, it's got a price, it's got a level, these are fields, and there's the actual structure itself. So you define a way to send the data from the grid to the goal routine and a method to send it the other way around. And then you can push data in and out. And if everybody has the same definitions for fields, it's dead easy. Node.js can write, Golang can read, other way around, whatever you like. So if we run that, we have retrieved almonds. It had the value 50, it now has the value 49. Let's run it one more time. We've retrieved it, it had the value 49, it now has the value 48. On one of the grid nodes, it will also, there it is, it's detected that the almond level has changed from, the level was 49 and now the level is 48. So all good, that's great. You know, we can retrieve data, we can change data, or we can save back. No, yeah, that's good. We'll come back to that one in a second. And now I mentioned, why did I keep typing cat? Now what we want to do is a bit of querying. So this is our query. We want to find all the nuts whose name contains the letter N. In this case, that's a case sensitive one, so it's N in lowercase. And what that gets us back is we're looking for entry sets, the map entries, keys and values that match that predicate. So the ones that this evaluates to true. So what we find is that walnut has an N in it, pecan has an N in it, because not exactly surprising. And there's almonds, it's got the value 48. So that's kind of good. We can do that querying, which kind of introduces the problem on the previous example. If we just look at that again. So what we do is we read the value from the grid into the Go routine. We update it in the Go routine and we save it back to the grid. That's nice and simple. It has one problem. The one problem, well, in fact, it's two problems. What if somebody else changes that data? We've read the value 49, we change it to 48. We want to save it back and somebody else does the same. You know, does their change overwrite our change? Does our change overwrite theirs? Well, it's kind of whoever gets there last, but you know, you really don't want that at all. If you're concerned with two things mutating the same data, then that's not a great approach. And then obviously you have to pool the data across the network, which depending on the data size may take a certain amount of time. So what's a better approach perhaps is a thing called an entry processor. So this is like our stored procedure. This is code that runs on the server side and updates the data. So let's do that now. And let's have a look at it from Go first, and then we'll have a look at Java and we'll run it. So we do the same thing before. We're getting our key is called almond. We're creating a stock decrement item, and we're saying we want to reduce the value of the stock by 5, and we execute that code on the item with the key almond. So what that means in effect is we want to change the stock level for almond by 5. We don't care from the Go routine what the current stock level is. What we get back is the new value, which we print out to screen. So let's try that. So we have now got the value 48 is our result. If we run it again, sorry, 43 was the result. If we run it again, we get 38, just to show that my maths are okay. If we run it again, we get 33. So that is reducing the level of the almond stock. If we look on the grid, we'll see that almonds are now down to 33. And let's have a look at how that code actually works. So, well, there's routine 6 is shut down. We don't need that anymore. So what we create, where are we? Here we go. Here's our stock decrement structure. So what we're sending from the Go routine to the client is a number. This is the number we want to change the value by. And then we have a way to send a value in, read a value back out. Dead easy. So we can transmit data backwards and forwards from this Go client to the grid. On the grid side, let's have a look at how that code works. This is Java code, so you won't necessarily understand it, but really it's easy enough. So what the stock decrement processing does on the server side is it gets hold of the stock value, it takes the stock level, it subtracts the amount we have sent, and that's the new stock level, and then it saves it into the grid. And what it's doing here is it's returning us the value that we've saved to the grid. So we don't return the whole stock. We don't need to know that it's almonds because we knew that already. We don't care about the price. All we're doing is reducing the value. Now, because this is coding, we could be a bit cleverer and not allow the stock level to reduce below 0. You know, you can't oversell almonds. So that's a thing we don't want to do. So what we have there is a way to change code, change data in situ. So because that runs in Hazelcast's grid, Hazelcast grid is in charge of the sequencing and makes sure that your code doesn't run at the same time as anything else. So you don't have to worry about concurrent updates. It will run your code, then run the next thing. And if your code has got a check that says, don't reduce stock below 0, then it won't go below 0. So that's nice. And then the very last example we have here, we're always concerned with efficiency in Hazelcast. It's all very well to do individual reads and writes, but sometimes you want large amounts of data. So what we can do is we can do a bulk retrieval. We want all the things in this array. So it's an array of keys. I want cashews, coconuts, and walnuts. Get me them all in one operation. So if I run that, then what I get back is cashews and walnuts because there aren't any coconuts in this shop. But what that means is I've done one operation and retrieved multiple items of data. And obviously there's the counterpart for writing. You can do a put all too. So that kind of ends the demonstration. So on to the last part. Oh, we've seen this already. So that was the demonstration. The summary, you can get Hazelcast in-memory data grid from hazelcast.org. You can get the Golang client from GitHub. Version 1 was launched in January, so that's got the core features of maps and queries and so on that we just demonstrated. We have a version 2 coming later this month, March 2018. It'll have things like queues and topics. And gradually we'll add all the other parts in. And if you're interested, there's a link there on Hazelcast clients and languages, so you can track all the things that we're adding into the client to make it fully featured. So that's it. Thank you everyone for watching. If there's any questions, fire away. Following that, we'll end.